Hello, class. This is Mr. Lehman. Day 2 of notes on empirical formulas, molecular formulas. So we want to work through an example problem today. Yesterday in your notes you had the step-by-step process that we sort of summarized as we worked through 2 problems. But let's take a look at this now that we have a little bit of working knowledge of the process. So once again, step 1, you're trying to calculate the empirical formula of a mystery compound. Step 1 is we want to calculate the number of moles of each element present, and we do that by dividing by the molar mass of the element. So if you're given the number of grams, you divide by the molar mass to find out how many moles of each element you have. So we have to know how many moles we have so that we can find the empirical formula. So step 1 is always convert into moles of elements. Number 2, compare moles of each element and divide each by the smallest to get the smallest whole number ratio. So once you figure out how many moles of each element are present in your mystery substance, whichever one you have the smallest number of, you're going to divide all your mole totals by the one that you have the smallest number of, and this establishes your empirical formula. That's assuming that you end up with a whole number, or it's very close to a whole number. So for instance, if 1 was like 2.97, that's close enough we could round to 3. Or if you got like 3.02, like that's close enough we could round to 3. But sometimes we're going to get numbers that are not close enough that we can't round to the nearest whole number. So here's some common fractions we're going to look out for. So for instance, if you got like 3.25, that would be 3 1/4. What you'd want to do is you want to multiply all your numbers by 4 to convert that into a simplest whole number ratio, because we can't end up with 3 1/4 atoms in our chemical formula, and we can't just round this to 3. So what we want to do is we'd multiply everything by 4. If you had like 3 1/3, you could multiply everything by 3. That would give you 10. That's a whole number. If you had like 3.5, you could multiply by 2. That would give you 7, a whole number. So these are the common fractions: a half, a third, a quarter, a fifth, a sixth. These are the common fractions to be on the lookout for. And the values that you calculate for each element indicate the ratio of elements present in the compound, and this becomes your subscripts in the empirical formula. Another tip today is if you're given mass percentages, and you saw this in one of the problems you did on the homework, if you're given mass percentages, then the easy thing you can do here is assume that you have a 100-gram sample of your substance. So what I mean by that is if by weight a chemical is 42% magnesium and 58% nitrogen, then just assume that you have 100 grams. If you have 100 grams of your mystery substance, that 42% of 100, that would just be 42 grams. And then 58% of a 100-gram sample, that would just be 58 grams. So if you assume you have a 100-gram sample of your mystery substance, then just convert your percentage sign, convert it into a gram symbol, and boom, you got your masses, you're ready to convert it into moles, you're ready to find your empirical formulas. So here we go, our final problem. We're going to work on example 5 in our notes. And we decided we're not going to do the hydrate section, so this is the final problem of our Unit 9 packet that we're going to do together. So it says we have an unknown compound, we're going to analyze it, and once we analyze it, we figure out that the composition of our mystery substance is 55.16% carbon. So just assume, it's percentages, right? Assume that you have a 100-gram sample of it. So 55.16% of a 100-gram sample is 55.16 grams of carbon. Alright, what else do we have present? We have 8.1% hydrogen. So assume that you have a 100-gram sample, that would be 8.10 grams of hydrogen. And then finally we got 36.74% oxygen. So we're going to assume we have 36.74 grams of oxygen because we're assuming we have a 100-gram sample. Next step, and let me space this out a little bit here so it doesn't be all scrunchy on us. Alright, so we're going to divide each by the molar mass. Alright, so I'm going to put these over 1. And we're going to multiply by the conversion factor. For oxygen, 1 mole of oxygen is 16 grams. And then for hydrogen, we're going to multiply by 1 mole is equivalent to 1.01 grams. And then for carbon, we'll multiply by the conversion factor. 1 mole of carbon weighs 12.01 grams. Alright, so we're basically dividing, right? So 55.16 grams of carbon divided by 12.01 grams. That's about 4.59. So we have 4.59 moles of carbon present. Let's take a look at hydrogen. 8.1 divided by 1.01. That's equal to about 8.02. Get ahead of myself here. That's equal to about 8.02 moles of hydrogen. And then how much oxygen do we have here? Well, 36.74 grams divided by 16. That is equal to about 2.29 moles of oxygen. So remember, now that we know moles, we can compare. We can't compare mass to mass because different elements have different masses because of different numbers of protons and neutrons. But here we know moles. So we're going to divide everything by the lowest number of moles. What we have the lowest amount of is oxygen. So we're going to divide everything by 2.29 moles. And then we're going to try to establish the empirical formula here. So 2.29 divided by 2.29 is 1. So we got 1 oxygen in our empirical formula. Look here for hydrogen. Hydrogen, that's roughly about 3.5. 8.02 divided by 2.229. 2.29 is about 3.5 hydrogens. And then carbon, this is really close enough that we can round to 2. But here's the problem. Look, 3.5, that's not close enough. We can't round to 3. We can't round to 4. We can't round to a whole number here. That's a half. That's 3.5. So what you can do here is you can double everything. We're going to double everything to give us whole numbers. So if you end up with a half, double everything. And so we're going to, let me rewrite this down below, give us some room here. So let's double everything. So we would have, instead of 2 carbons, we'll have 4 carbons. Instead of 3.5 hydrogens, we want a whole number. So if we double it, we have 7 hydrogens. And for oxygen, instead of having 1 oxygen, because we doubled everything to get rid of the half, if we double it, then we would need 2 oxygens. So here's our empirical formula. C4H7O2, that is the simplest whole number ratio between the elements in our mystery substance. And that is all the questions asked us to do. All right? But let's say we have one more step. Let's go above and beyond here. Let's say the molecular mass, the mass of the whole actual chemical, let's say the molecular mass is 261 grams per mole. What is the actual chemical formula? So once again, let me scroll down here, go a little bit more. Remember the formula that we use. We're going to take the mass of the whole molecule, that goes on top. So the mass of the whole molecule, the actual molecule, goes on top. And we're going to divide that by the mass of the empirical formula. So let's just get a rough answer here. So we have 4 carbons. So 4 times 12. Let me get my calculator out here. 4 times 12, that's 48. And you have 7 hydrogens, about 1 apiece. So 7 times 1 is 7. So you have 48 plus 7, that's 55. Plus 2 oxygens, that's 16 each, that's 32. So we have 48 plus 7 plus 32. That is equal to 87 grams for the empirical. When we divide the whole actual divided by the empirical, it gives us what we call the multiplier. 261 divided by 87 is about 3x. So this is our multiplier. So what would the actual chemical formula be? We're going to triple the empirical formula. We're going to make it 3 times heavier. So if we triple it, the chemical formula of the actual molecule is going to be C12H21O6. And there you go, guys. That's it. That is our chemical formula. Alright, so finish up pages 13 and 14, and if you have any questions, send a message. I'll be checking my computer throughout the day. Alright, have a great day, everybody.